Hello, it is Mike Levin on Saturday, February 27th, and it is time to talk about concurrency. On my last video, where I set up some Jupyter Labs keyboard shortcuts, I gave you a quick introduction. I'm doing some retooling, and in the process of that retooling, it's time to replace the requests, the incredibly popular and influential in the Python community request package with the new HTTPX package, which claims to be API compatible with requests, but also able to handle true concurrency without requiring a type of threading, which might give you concurrency, but not performance, because there's a deep story here. You want packages that were coded intending to be concurrent these days using the new standard library async.io that's built in to Python these days. API compatibility, this is a wonderful example that if you pick your everyday tooling carefully, even when the underpinning technology changes, so long as you have API compatibility, in other words, the way you use the commands, you have taken a major step towards future-proofing yourself. This is a payoff video of having taken that approach for so many people in Python. The fact that new libraries can burst onto the scene using the same API. Now, the example I found, I am generally not a object-oriented person, nor am I usually a concurrency person. But this example from the danielms.site is enough to make me change my mind on perhaps both fronts. Certainly when I take up object-oriented again, I'll be taking this nice simple example up to remind myself how to do it well. I can give you kind of a quick overview, but what we're really doing is searching for the magic fairy dust that does something like MapReduce. So you'll hear MapReduce thrown around all the time. Back in the day with Google Bigtable and Hadoop busting onto the scene, it was such a big deal. So things are normally concurrent and they go one at a time, with this circle representing a certain amount of resources consumed by the CPU that can't actually happen at the same time. It's called CPU bound. You have one CPU, you can have one thing filling that slot. And this is the traditional sequential method of programming, which came to us as a result of the CPU architectures of our modern day, or of ye old day, because it's not that way anymore, because resources were constrained, because you couldn't throw a ton of cores into the same processor. Now, say you have 8 processors. Now, forget about, concurrency the way it's often thought about, with an unlimited number of tasks being able to be broken out. We're going to talk in terms of CPU because that's true parallelism. There's 4 slots that are able to be used. Something is sent to a step that does the mapping. Everything is MapReduce, even though there's different words for it and different labels. So you've got a CPU, just let's say a 4-core CPU. The same task is mapped out over 4 different CPUs that can actually work in true concurrency. If this axis here is time, this little bit of magic here is true parallelism. And so each of these in turn has some sort of output. If this represents the input going into each of these, mapped out objects, there's also a result that comes back. I guess we'll draw it as a square because it is, something has taken a different form. It's oftentimes a response to some sort of request. And then there's a function that goes across it and brings it back down, and that's the reducing thing, because say you are summing it, some sort of aggregate function. Aggregate functions oftentimes are the reduction, and you come back out with your result out the end, except it happens when people say, you know, they get a 10 times speed increase. That's where it's coming from. It's coming from true hardware parallelizing. There's some funny words there. And, you know, not from necessarily simple non-blocking I/O, which is a different technique to have multiple, you know, lines, but they're not going through real hardware processors, so you don't get the speed advantage. So we're trying to get that speed advantage here. And in this example of this wonderful object-oriented code, let me get a good size for giving you sort of a great compromise of overview and readability. I won't go line by line, but suffice to say he's importing not much. The item getter, that's one of the most interesting bits. I want to get better at the kind of thing he's doing with the item getter, but async IO gives the asynchronous, the parallelism. This gives you the old requests package in new form. And then you see a class is defined. So already it's a different style than I'm used to. So you're like, okay, oh, it's only one class. That's nice. Everything is inside of one class. I don't have to hold that much in my mind. And a new instance is being created of that class, and the internal method is being invoked called run. So we're going to look up here. Oh, you don't have to look far. It's run. So a new instance is being created, and then the run method is being invoked instantly, which means, oh, and then at the bottom, by the way, an internal object that gets populated as a result of that, of the HN object, is printed. So nothing is outside the object. It's really interesting. An object is created, an internal method is called. The state of the state inside that object that exists in memory changes, and you can then show it. So that's what's happening here. This makes run the entry point. It's very well documented. Run is the entry point. And then it does two things with internal. Whenever you see self, these are things that are actually, you know, functions or methods that you'll actually find up there. So if you see run async task, you won't have to scroll up very far to see run async task. And so everything is pretty well laid out. And the only other thing that maybe ought to be brought to your attention at the beginning is that def init is a standard under object-oriented Python, which you can identify by the word class here. When the word class is there, one of the conventions that is carried out is that everything inside dunder init that has at its disposal all the objects, it's self-referential. So inside this function, which is inside a class, which makes this called a method in popular Java terminology, but inside of the dunder init method, it has access to the whole object through the self-reference. So it's making an internal variable named URL equal to this, top stories from Hacker News. It's making an internal dictionary called container. It's making two internal lists, one called stories and one called responses. And then it's calling self.run as at the end of being called. So that's what makes that run function down at the bottom the entry point. The moment this function, a new instance of this function is created, the moment a new instance of that function is created, dunder init is invoked in run, and at the bottom of dunder init, self.run is invoked and run, which makes this, as he points out, the entry point. And then this internal function is being fed the output from this internal function. So story.metadata is being fed into as the input def run. This guy here is being fed to this guy here. Now we can see what kind of things are returned as a result, and this is where A lot of focus is going to be put, right? This is a lot of focus. So this is just a way of executing tasks. And what we're doing is we're looking for a certain sort of magic fairy dust. So to demonstrate to you how cool this is, I was able to pick up that exact code. I really just, here, I'll delete this, I'll get rid of the output. I'll cut that box and I'll paste it into that new box to show you just how impressive this exercise was to me. This almost never happens. You copy the full gist, and you could view raw. There's other ways to get it, but the fact it even works this way is impressive. So my first thing is I pasted it in, and then I tried running it. And I got, oh, well, it ran right away because it's all in memory. Let me do a Control-Shift-R, restart and clear outputs. I demonstrate my new keyboard shortcut, right? Restart and clear outputs. You should do that a lot when you use Jupyter Labs. Now you'll notice I haven't executed this top thing, and I execute this bottom one, and I get an error. And I recognize this error because I started to take up asynchronous coding, but I made the mistake of doing it in Jupyter Notebooks/Lab. So I saw this error a lot. I researched it, and I learned about the event loop that's always running, and a REPL environment kind of wreaks havoc on it. And you got to change your technique a little bit. That is, until I went researching it again, and how things change so quickly on the net in just a matter of, a month or two since I last researched it. Just use this. And this person points you to this article that, well, it's not an article. He points you to this GitHub repo, a very useful repo that addresses this problem directly. By design, async IO does not allow the event loop to be nested, which is a problem in applications like Jupyter, because the event loop is always running. It's never not running, just like the rest of the code in Python. It's just never not running. That's why the variables hang around for so long when you're done. So I was able to just do this, and now this, I'll go near the bottom so you'll see that wonderful output go out there. It works, right? This is the top 20 stories from Hacker News, and this is where our story begins. I love this code. There's some other libraries, by the way, out there. There's probably a ton of them by now. As things are in the Python community, you can at this point choose between HTTPX, which I'm using, versus AIO HTTP and a whole bunch of other things in the AIO series. That is turning out to be a quite popular set of things. However, and higher performance. They say, if you're looking for how many thousands of HTTP requests you can make per second, you might want to go to AIO HTTP or the Go language. However, if you're just interested in getting into the concurrency world, getting a ×2, ×10 increase, but not tweaking it out to the max, and you want to preserve all your, past know-how and try and continue your future-proofing yourself and demonstrate to yourself what a good idea it is to choose popular libraries with popular APIs that will never be let to die. That's what's happening here. So, in this output object, I recognize this. It's just a bunch of JSON shoved into a list. And the transforms, he does his own method of transforming, but when you have a bunch of JSONs shoved into a list, there's a bunch of ways to get from that to more useful data. And this is one of the things I'm going to learn from. He's using native Python objects with key item getter score to sort that by the score inside of there. It's fancy stuff. It spares you from having to even dust off SQL or anything for manipulating fairly complex objects natively in SQL with just built-in stuff. It's really amazing. However, I do know that there's an easier to grok way if you don't have to sort by some internal key value pair. But he's printing hn.stories. And see that square bracket there? That means you're sitting on a list. So if I scroll down to here and I put that in, first I can confirm for you the fact that is a list we're looking at. I mean, it's a list. Even though it looks like this complex thing, square brackets at the beginning and end, that's your indication. You could even check the length on it. It's top 20, URLs from Hacker News right now, so that only makes sense. I can go a little bit bigger now for the sake of the audience. I'll turn off that side bracket and take a deep breath. When you've got a list of JSON objects and your keys are all at that top level, which you can kind of see there, you can do list comprehension. So you take again that list name, and list comprehension starts out by taking a list and putting square brackets around it. And then you can simply do, if I were to execute that, there'd just be 2 square brackets as a nested list. But if you were to put x for x in, execute that, you get back to a normal list, except like lambda functions and a bunch of other things that work like this, by having a built-in iterator on an object, it exposes a handle on an item as you iterate. And then you can use a key because you have a handle. Get a handle on that. If I wanted to show the by of every, whoops, it's of course got to have quotes around it. There's the by. You can see a lot of duplicates in there. There was, in fact, a URL field. Let's take a look at that. That'll be helpful. But there's our duplicates again. So instead of list comprehension, how about some set comprehension? Replace the square brackets with curly brackets, and it just automatically dedupes. And I want to check the length of that because it's certainly less than the top 20. It's 10. It dedupes down to half the total amount of articles. Oh, well, let's turn that back into a list. Sorry if it's hard to follow along, but by putting the word lists there, I am leaving the parentheses that were in place from the length function. And what I'm doing, for people who didn't just follow that magic little bit, this is an alternative way of doing simple list comprehension, which used just square brackets at the beginning and the end. But this lower version versus the upper version uses curly brackets here, which turns it into a set instead of a list. So it's set comprehension. You can also do dictionary comprehension if you use 2 handles out here, one for the key, one for the value, inside parentheses to make it a tuple. However, we want set comprehension, so it does the deduping naturally, and we want to turn it back into a list because we're going to iterate over it. And now that you see you got a nice clean list of 10 URLs, we'll give it a more friendly name. We'll say URLs equals, and now we can use that in, say, subsequent list comprehensions, because we're going to import the request library, good old friend requests, in which you know how to do many things by heart now because it's gotten into your muscle memory. The world went concurrent. You want to take requests away from me? No. It comes back in the form of HTTPX, which you are going to have to pip install or conda install. They say the common wisdom when on Anaconda, use conda. So you would, oh, that's a plus for that. Shift B to bring back the plus I need, which is that. You can go down to terminal, and from here you can go conda install HTTPX because it's not already installed under Anaconda. When you joined me on this video, it was installed because I had already done this and did not bother to remove it from my machine for the sake of the video, but I will show you doing the conda install under a terminal tab so that you can understand the prerequisite to this project, because the next, you wouldn't even have been able to run this block of code. I wouldn't have been able to run this block of code up here if HTTPX were not installed. Everything else is pre-installed. Amazingly, Nest _async IO is pre-installed. That's either part of Anaconda or it's part of one of the other things I installed, which is not much right now. It could be part of this, but this allows asynchronous. This is some magic fairy dust that allows asynchronous behavior to work under Jupyter Labs, probably Jupyter Notebook as well, taking care of event loops can't be nested, and therefore there is one main one always in Python, so it fixes that problem. Speaking of magic fairy dust, you'll remember as I was scrolling over on this side, I was really slowing down and taking a look at the part of the code that was very enticing, because me sees the HTTP. Well, no, I didn't really see the HTTP object there. I saw context. Well, here's some return. Oh, wait, no. Story metadata, async with. With the context manager. Boy, do I need to do a video on the context manager. That with keyword is a wonderful thing. It's another way. I already mentioned 2 ways to expose handles to things. This is another way. Whenever you see the with operator, they're opening something that has some sort of connection to it that's going to need to be closed. And the with operator means when it gets out to the bottom and goes back to that outdent level, there's the automatic housekeeping. The finally, the try finally close stuff that's implied happens, and it cleans up nicely after itself. I also see an instance of the async client being made. And from my research, I know this is the equivalent of the requests session, when you need to hit the same website over and over with a lot of the same, scaffolding of your connection not being destroyed and recreated all the time. You want to reuse it. So, cookies, don't go away between requests, all kinds of stuff. So this creates a sort of consistency between requests. I recognize that. And forget about Logger. This is really interesting. I was telling you I was about to import requests. It's because there's a pattern we use here that I see, that I recognize. What is that pattern? Well, we go to the bottom. I'm sitting on those 10 URLs. Well, when you're sitting on 10 URLs like that and you want to use requests, it is requests.get for an individual URL. You remember, any one of these. So we have URLs in there. If I were to put URLs and then an index of the first URL, this would be the output of the page. Requests, I got to use plural. That's the response object from a single request. If I wanted to look at the text of that, that's the text on the page. It's a standard way to do web crawling and stuff. So the requests.get is really powerful, but remember that list comprehensions? You want to do it for every URL there, and if you're not looking at the text, it shows as this nice little response object. So follow this. If you don't do stuff like this, if you don't work this way yet, you ought to think about it. It's a list. Now it's a nested list. X for X in. Now it's a list again, back in its exact original form, but you've exposed some internals with an iterator, a for loop. And once you do that, you can do anything to any of these elements on that. Again, this is similar to patterns that reoccur over and over throughout Python, where you don't have access to such internals on an object and you're given access to it with something like this. With open as, after the as does that, the lambda expression does it. And what are we going to do? Well, naturally this. We're going to pick this up. No, we're going to put this right here, and then we're going to paste the close parenthesis right in there. And when I execute that, instead of a single response object, is going to be a response object for each one of those. Now that poofed away. It's not actually in memory, but you get to see it in the output. If you want it in memory, you go, responses equals that. And now it's like a crawl. That was a little crawl of all those 10 pages. You're sitting on top of a response object, and you could look at the text inside of any one of those. And you saw it took like a moment or so for that to actually finish making all those requests. With only 10 URLs, it really doesn't take that long. However, this is a sequential pattern. It's doing one after another. The honest truth is, if you had something like Dask running as your, parallelizing framework, your map reducing, running interference piece. I see a map reducible piece. I'll spread it out over as much resources as I have. So this could be parallelizable transparently. There's a number of ways in Python that's accomplished, but we're going to do it in the way that, gives you deliberate control. You're sitting in front of it, looking at it, and it's got to be this, right? This is it. Now there's some other interesting things here. So I can recognize the list comprehension, right? That's 2 square brackets. The X for X in, that's list comprehension. That's being fed into a function or method. It's being fed into the gather method of async.io, a standard library thing. This is where you would find such things as MapReduce types of functions. This, I'm going to guess, gather. This little guy here is very insightful. That is an asterisk coming before a list comprehension. So this is generating item, 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 item. This asterisk here is saying, send all of that as input to this function. What? Well, this guy has some serious kung fu. His object-oriented methodology combined with his way he, invokes things and passes parameters, and it's beautiful. It's beautiful. I'm going to keep this bookmarked and learn from it quite a bit. This guy here is what we're going to try and turn this into here. That's a distraction. So I'm going to say a response is equal. No, I'm not going to say it yet. I'm going to try and do it so you can see it without me setting it to something yet, so you can see it raw, just like the way I did there, right? Let's just copy and paste it and rework it. Oh, maybe? I don't know. Okay. It definitely, this is the magic fairy dust. There's no doubt about it that somewhere in here is where the magic happens. And I'm going to try and not switch myself completely into async mode, although the second you use async, you're in this asynchronous mode. I'll try and keep it as simple as possible instead of not switching myself into asynchronous mode, which I can use object-oriented. He contains it in object-oriented programming, so that does not slip out into this context. He could continue with sequential programming methodology there. That's very appealing. That's the strongest argument I've had yet for OO in Python for my kind of jobs. Okay. We keep in that. That looks really good. That's our context manager, async mode with opening a client connection. Forget about the logger. We're not going to need that for our purposes here. That's too much indenting for readability. There's no self because we're not in object-oriented mode. We're not going to want the something equals to something because I want to expose it visually. And this is just a convenience of knocking it down to the next line. Suddenly the readability skyrockets. I can almost use this in its current form. We're not going to do self.fetch. He wrote a function to do that. My main question is whether I'm going to have to use the await keyword yet another time. I don't think so. So async with as client. So let's just type that raw so we understand it. Await async io syncio dot gather. Ooh, that sounds powerful. I don't even need to do that yet. I can do this inner part here, can I? that is a fetch of an HTTP. Fortunately, we don't need that extra list comprehension there, do we? We're starting with URLs, and we're going to be doing request.get. Let me repeat it. X for X in URLs. But instead of request.get, it's going to be httpx.get. And you would say, if they're so similar, why are you not just using requests in there? It's because the internals of this are different from the internals of this. And the internals of this are built to run in this context better. Moment of truth. You remember how long this took? Generally speaking, okay, it's not long, but, you know, say there were tens of thousands of URLs you needed to get. This one here won't run without being in that context, so I can't just execute that. That would fail. Or would it? Holy smokes. Wow. Okay, well, it did succeed. Maybe it was running sequentially. Let's put it in asynchronous mode for real. And we can't forget to splat. Boy, I should really demonstrate that. I know to put it in. Yeah, okay. Required. Async coroutine or awaitable is required. So I did miss an await or something somewhere. Okay, I figured it out. After going back here and studying the source code for a bit, I went back to the fetch function. I just made some assumptions about that, how that HTTPX get was being accomplished. And looking here, I saw the word client instead of HTTPX. And I'm like, oh, no, I have a handle to the client, the async client method or function of HTTPX. I'm inside the context manager. I don't want to use something from outside that context. I have context. So we just replace HTTPX with the word client. And we have success and we have speed. So we can do a little speed comparison now. This is the big payoff. Get rid of this one. That's just noise. But this is the old, oh, and we'll also put some word in here, right? So A responses. These are the asynchronous responses. Okay, so here's the old way. All right, not bad, but here's the new way. Instant, whoa. A responses equals helps to have equals. Of course, an error is instantaneous. Still not bad. And then we'll show it like the way responses is shown here, because it's the last line. Because of that indent, apparently it isn't the last line, but we can take advantage of Jupyter Labs doing it that way. So, oh, it isn't really showing it. I'll put it here. 10 response objects sequentially. 10 response objects asynchronously. There you have it. Okay. So I will do a tiny bit of editing to just get rid of that little bit of stumbling at the end, but it was just about as straightforward as I had imagined. The pattern changes a bit. A simple one-liner to populate a response object with a bunch of requests using the old list comprehension trick. Is reliable, great for spidering, so long as you're not too many URLs, you'll run out of memory on your machine. New pattern. You can't get away, it seems, unless you want to use much more complex asynchronous programming with callbacks and promises. You really can't get away from the async and await keywords. So since you're going to use it anyway, it feels like it's a lot more legit now, because it just feels like overhead to me. After you throw all these async awaits to make, concurrent code run asynchronously, which is what you're doing. You're awaiting stuff to happen. If you're going to have to do that, you might as well have the line that has the await doing something that could be massive so that it's following a path like this. You want to see something like this in your process for it to be even worth doing concurrency, a map reducible process, which is also, you know, very frequently you see that in the square brackets of list comprehension because it's got to process every item in a list. And I'll be able to grok that. I'll be able to grok that. It's not so different. Gather, that's a good word. You send it the members of a list not as a list object, but as separate inputs, as arguments. And I guess I'll finish that up as the last thing here. The video is running a little bit long, but if you don't understand argument splatting, you're not getting what's going on here. I spent a good bit of time on list comprehension. Async and await I'll spend a little more time on. Context sensitivity I'll spend more time on with open. That's coming up in a video. But splatting arguments, let's define foo, and we'll give it one parameter, x. Return x. We got a function, foo bar, returns bar. However, if you wanted to feed it a list and have it return the list exactly as it was fed in, but not to give it a list as a single argument, but to support essentially x, y, z, and so on indefinitely, you can just put an asterisk in front of the x. Now it's returning it as a tuple. See that? Or a tuple if you prefer. Now if you give bar blah spam and eggs, guess what? It's going to come back. But no one wants to write it out like that. You're in Python, so chances are in some area above that function you will have populated a list with all that stuff, given it some, you know, arbitrary variable name. And now you can feed that variable in there, but not exactly, because it's going to come out a list. You want it to come out a tuple, which is not enclosed as if it were one, you know, object being fed in. We unpack the tuples on the assignment, and bam, it's as if it were fed in as those separate objects. So that's the functionality of the splat operator, an asterisk at the beginning, which we see in the original code. It was weird to see it here. I'm like, wait, an asterisk before list comprehension? What's that doing? And my eyes had to piece it all together, going, oh, this async IO library must have a gather function that takes an unlimited number of input parameters and treats it in a map reducible format. The function is called gather, so big surprise. And this is going to change my working pretty much forever. This is about fundamental tooling. This is about the things you reach for every day. The request library is HTTP requests for humans. I reach for it every day. It's in my muscle memory. And now to do concurrency, I got a slightly new pattern to get into my muscle memory so that this kind of stuff comes natural. You got a list of, 10,000, 100,000 URLs. You can get them concurrently. There's going to be ways to throttle it. You don't want to try and get 100,000 URLs against the same website all at once. It's called a denial of service attack, except, there's ways to throttle it. So you can always speed up your work using these techniques. It's worth taking on concurrency if you can, use it like with scalpel-like precision so that your whole code base doesn't become unreadable like sequential code that you just littered up with async awaits because one line somewhere needs to be in asynchronous mode. Anyway, thanks for joining me. Hope to talk again soon, and don't forget to subscribe.